Hey, it's Jim, and this is level 1 of the CFA program, the topic on quantitative methods and the learning module on simulation methods. I'm guessing that you guys are very familiar with simulations. They're done before World Cup soccer events. They're done before US Super Bowl event in February. Those of you who are interested in climate change and read the Wall Street Journal will know that simulation models predict temperatures decades in advance. The question then becomes, how do we use that familiarity and apply it to our portfolio management? We'll do that inside of this topic of quantitative methods. Of course, what's a logical outcome is to simulate the performance of a client portfolio. Oh, this makes perfect sense. If you look at the LOSs, we're going to talk about Monte Carlo and Bootstrap simulation methods. We'll do that in the last 2/3 or so of this slide deck. But what the learning module tells us at the very beginning is that in order to understand simulation, we need to start with normal and log normal distribution. So that's what we're going to do here. Now, I'm guessing that you've seen that left bottom picture 100 times, maybe 1,000,000 times. That's a picture of a normal distribution in which the mean and the median and the mode are the same number. Notice that we have the two words zero skew. There is no skewness in a normal distribution. And the left side of the dotted line is symmetric to the right side of the dotted line, which tells us, and this is really important, that to describe a normal distribution, all you really need is its mean and its standard deviation. Now, in finance and in portfolio management, we try to make assumptions about the distribution of the assets inside of the portfolio. So it makes sense to ask the question, what kind of a distribution do bond returns, do alternative investment returns, do stock returns follow? Well, it's super easy if they follow a normal distribution. And once we get to level 2, we'll talk about different kinds of distributions, and we'll have lots and lots of good tests to decide about the distribution and then what to do if it's not a normal distribution. But here in this introductory learning module in level 1, what we're interested in knowing is simply that stock returns, they tend to follow a normal distribution, which means, and you know this, that stock returns can be positive or negative. Well, what about stock prices? We know that stock prices can't be negative. We know that alternative investment values can't be negative. Maybe bond prices can be negative in some rare cases, but clearly we need to ask ourselves the question, what kind of a distribution do asset prices follow? And so this is what we know. We know that if continuously compounded asset returns follow a normal distribution, then the prices of those assets will follow a log normal distribution. And that's the picture on the bottom right. Notice that the origin begins at 0. So you can't have a negative asset price. What we're going to do is we're going to have a distribution that is skewed to the right. We can call that positive skewness. Now, a couple of other things about this log normal distribution. Its mean is probably going to be greater than the mode. Let me go back. If you draw a dotted line from that top point of the mountain, that would be the mean. The mode is probably going to be somewhere to the left of it. Now, here's the really cool thing about this stock returns and stock prices. Normal distribution, log normal distribution. Look at that second pill point. That both distributions, whether normal or log normal, they can be fully described by just the mean and the variance of the normal distribution. Now, for those of you who are mathematically inclined, I encourage you to type in a search and say something like, hey, how do you derive the mean and the variance of a log normal distribution? And you'll get those equations that we have down there in the box. So just remember that the mean, the mu sub L, is equal to, that's the E raised to the X. Now, raised to the X here, we're going to put the mean plus 1/2 of the variance. Now let me go ahead and pause and just warn you that the mean plus 1/2 of the variance, that's going to be a really important concept as we move through portfolio management. We're going to do some maximizing and minimizing, and so we're going to come back to that. But for now, let's just take my word for it and say, okay, that is going to be the mean of a log normal distribution, and then the variance. Well, those of you who typed in already the derivation, you'll see that, boy, it takes about this much space on a web page. But the important thing to remember is that that's e raised to the x. Now, we did this back in a previous learning module. Remember, I had you get out your calculator and find your little e to the x button. Remember, I called that Euler's number. That's 2.718, and then it has a bunch of, maybe it has a million decimals after that. But there's a mathematical constant, and that's relevant for our normal and our log normal distribution. Now let's go back to this continuously compounded rate of return. What did I say just a moment ago? If asset returns, if the continuously compounded rate of return on an asset follows a normal distribution, then its prices follow a log normal distribution. And so this is super important, because what we can do is we can take this distribution and we can use it to compute. How about if we simulate the future value of a portfolio? What we're going to see sometime in level 1 and then again in levels 2 and 3 is we're going to look at an objective function, and we're going to say something like, hey, let's maximize the end of period wealth. And of course, the end of period wealth for our client might be maybe when that client retires, or maybe when that client expects to pass away, or some other date. What we can do is we can use this log normal distribution to go ahead and compute the end of period wealth, the future value of our client's portfolio. So you see how all of this is interrelated. Future values of portfolio, so we need to make decisions today that are in the best interest of our clients so that we can maximize their end of period wealth. To understand that, we need to know about normal distributions and about log normal distributions. So look at the bottom gray box down there. I have an example here in just a second. In order to compute that expected value, all we really need to do is just some super simple math. There's the variance of the distribution, sigma squared times t, and then if you take the square root of both of those, you get sigma times the square root of t. Let me tell you just a quick story. That when I was at a conference in Chicago, this is years and years ago, with a bunch of college professors, and we talk to each other and we discuss our research, and we were talking about the Black-Scholes-Merton option pricing model, and whether stock returns follow a normal distribution and whether stock prices follow a log normal distribution. And we were talking about this. And one of my older colleagues made a comment. He looked at me and he goes, he says, you know, Jim, standard deviation moves through time at the square root. And I thought, boy, that was one of the coolest things that I ever heard. So just remember what my colleague said. So the standard deviation, you take the square root of the variance times the square root of time. Thank you for indulging me there for that minute. All right, here's that end of period wealth formula that I was telling you about just a moment ago. So PT, that's the future value of our portfolio, end of period wealth. That's going to be the present value today, P sub 0. And we're going to multiply that by E raised to the R over some time period. So there's our little E to the X button. We're going to use that knowledge to predict knowledge of continuous compounding, knowledge of log normal distributions, to be able to have a better sense of what that end of period wealth is for our client. And of course, that's a super important relationship that we have that is conveyed through the policy statement with the client. The client sends us a bunch of money as good portfolio managers and says, we don't know what to do with it. Here, you take it. We have these objectives. We have these constraints. And then we can use our knowledge of all this stuff that we're talking about to have a better idea and make a more accurate prediction of that end of period wealth. I mean, the last thing we want to do is tell our client, oh yes, when you pass away, you're going to have $5 million. And that's based on nothing more than flipping a coin or doing something crazy. Of course, we're basing it on fundamental statistics, fundamental economics, fundamental accounting, fundamental investments. Boy, that sounds an awful lot like all the study sessions that the CFA Institute wants us to know. All right, so what we just did there, I showed you the equation and we had some discussion on continuously compounded returns and future values. But what about standard deviation? So we can go ahead and we can annualize that standard deviation, and we're probably going to do that over 250 days a year. Actually, when I was in graduate school, when I was writing my dissertation, my professor, my dissertation chairman, he suggested that I do this in 252 days a year because that's the exact number of trading days, not 250. But the Institute wants you to remember 250, so that's probably what you'll use. All right, so all we're going to do is, what did my colleague say? Standard deviation moves through time at the square root. So if daily volatility is 0.5, then annual volatility, we just take the square root of 250. By the way, I learned a tremendous amount from that colleague who taught at a regional school in the Midwest. And I always look forward to visiting with him because he always had something really, really cool to say. Sometimes about finance, sometimes about other stuff. All right, let's work through a quick example. And this is important. There's an example inside the learning module. And this is one of the questions at the end of this learning module. So you have 3 of them from which to practice. So this sounds like an awful high probability question on the exam. All right, so here we have Monday, Tuesday, Wednesday, Thursday, Friday, closing prices. So we start at 75, then we go up, but then we go down every day. So what kind of a conclusion can we make from just this weekly observation is that if you bought on Monday and you sold on Friday, it wasn't a good week. But let's go ahead and ask the question, what is the first moment of the distribution? What's the mean? And then what is the second moment of the distribution? What is the standard deviation? Now remember here, these are daily prices. All right, so let's go ahead and do the math. I showed you this in a previous learning module recording. Go ahead and get out your financial calculators. And we're just going to do a simple old F over P. Now, when we have discrete compounding, you've heard me say this before, and you'll hear me say this again, we'll just do F over P minus 1. So if we were doing discrete compounding, we would say 78 divided by 75 minus 1. And that would give us our discrete daily compounded return. But we're doing this continuously, so we're going to say F over P, we're going to say 78 over 75, and then we're going to hit our LN button on the calculator. So if you do that 4 times, right, we have 5 days, so you have to have n minus 1 returns, so 4 times. So you get, what is that? 39.22, and then 80.04, 28.17, 28.99. My advice is just to pause the recording here, make sure that you can compute those, because it's very likely you're going to have to do that on the exam. Once we have each of those continuously compounded daily returns, we probably want to take the mean. We want to take the average, right? So there's the first equation at the top of the second blue box. We're just going to solve for mu, and we're just going to sum those and divide by 4. We learned how to take an average in kindergarten. So what's that mean over there? Minus 0.24495. Of course, we knew, here, let me just go back here quickly. We knew that since the price went up a little bit, but then it went down 3 consecutive days, we suspected that mean daily return was going to be negative. So then let's go ahead and compute the variance of those daily returns. And all we're going to do is take the difference between each outcome. So the 39.22, the 80.04, the 28.17, the 28.99, and the 24.495. So that's what we have down at the bottom of the second blue box. And we square the difference just to get rid of the negative. And you sum all those and divide by 4, and you get 0.001795. Now look, let me warn you, you might be tempted to put those 4 numbers in the top blue box in your calculator and then solve for the variance. But you got to be super careful, because if you hit the sample variance, the calculator will divide by n-1 and not 4. So here you got to divide by 4. So it's probably just as easy to do this the long way. I can't imagine the Institute would give you, here, let me go back here. I mean, look, 5 days, that sounds like a reasonable question. I can't imagine the Institute would give you 7 months worth of daily returns. You know, you'd be punching away forever. So this sounds reasonable. So my advice is to go ahead and do it, you know, kind of the long way. Divide by 4, get the correct answer. So there's the variance. Next thing we need to do is get the standard deviation. So all we're going to do is take the square root, and then we're going to go ahead and annualize that volatility. We're going to take that 42,363, the daily standard deviation, and then transform that or annualize it by multiplying by the square root of 250. Notice that nowhere in the, let me go back here, nowhere in here are we told, hey, there are 250 trading days in a year. So that's the number that you'll have to remember. As I was saying before, what did my colleague say? Standard deviation moves through time at the square root. So there you have 67%. All right, here we go with the second and third LOSs. And this is really the meat of the learning module. But what I'm going to do is I'm going to go ahead and tell you a sports story here. And it's going to give you a great toolbox to answer the questions on the exam. So look at this. LOS is describe Monte Carlo. The third LOS is bootstrapping. So let's go ahead and go back to my original example at the beginning of this slide deck, where I said at the beginning of the World Cup, there are simulation models that predict the outcome of, you know, either the 16 teams or maybe even the 32 teams. Although I think I read that sometime in the late 2020s, they're going to expand that to 45 teams or 48 teams, whatever. So, all right, imagine we're in the World Cup final, and it's 0-0. They play the overtime. They play another overtime. It's still 0-0. We're going into the penalty shootout. Now, as you know, those of you who are soccer fans, I'm sure there are tons of you out there, that on the television, they're going to go to a commercial because the teams, they have to go to the sideline. They have to figure out which of the 5 players are going to kick. They got to flip a coin. They got to do all. So they go to the commercial. So they come back from the commercial, and the TV announcers say, while we were away, our analysts have performed a simulation. And according to our simulation model, Team A is going to win 77% of the time. Team B, we don't like Team B. They have no chance of winning, or something like that, right? So the question then becomes, how did they do this so quickly? What inputs did they use? Well, the first thing that you should know, and I probably shouldn't even have to tell you this, is that the inputs to the model are all relevant, right? Like the skill set of the players, the wingspan of the goalie. These are all super important variables. I mean, they're not going to take into consideration the stock price of a large retail firm on the floor of the New York Stock Exchange, right? That doesn't make any sense. But maybe they'll throw in weather. Can it snow during a World Cup final? I don't know. Can it rain? Can it be freezing cold? All right, so there are essentially 2 ways to do this. Are you ready? So just sit back and take a deep breath, and it's going to take me a minute or 2 to get through this. All right, so imagine a scenario like this. So what goes into that computer algorithm? What goes into the simulation? What are those relevant variables? Well, so let's suppose that we've got 11 players at the end of that second overtime, and so the coach can pick 5 of those 11. But inside of the computer model has to be all 11 of those people. So the first algorithm will be, all right, let's randomly pick 5 of those people, 5 of those players. And what's going to happen is that the input is going to be every penalty kick of every one of those 11, and then the randomly chosen 5, every penalty kick that these individual players have ever taken. Right? Some are right-handed, some are right-handed. Hello, McFly. Some are left-footed, some are right-footed. Sometimes they hit it to the right of the net. Sometimes they hit it to the left. Sometimes it's on the ground. Sometimes it's high. Sometimes it's wide left and wide right. Sometimes it's high. So one possibility is to take every penalty kick, every historical penalty kick that all 11 of those players have taken during their professional life. Couple that with the goalie. How many penalty kicks has that goalie defended during the course of his or her lifetime? Sometimes they block this way, sometimes they block that way, sometimes they block with their feet, sometimes they block with their head, sometimes they don't have to do anything. I mean, I've seen where the goalie just stands there, and sometimes the ball comes right to him or her and it's blocked, sometimes it goes out. All right, so this is what we're going to do. We're going to simulate. We're going to reach in, we're going to pull out one of the 11 players, and we're going to reach back in and pull out one of their historical shots. And then we're going to put the goalie there, and we're going to say, okay, we're going to reach in and pull out one goalie defense where the goalie goes this way and puts his or her hands up this way. Is that a good or a bad goal? We're going to do this over and over and over again. We're going to play this out thousands of times. And at the end, we're going to say, oh, Team A 5, Team B 3. Everybody get this? Now, notice that simulation is based on actual history. But suppose that it's possible that when we randomly pull one of these players out, that historically this player, when shooting for the top left corner, has hit one here and has hit one here. Both of them are good goals. But nowhere in the history has this player ever hit one right in between or anywhere in between. What if we could assign a probability distribution based on the historical outcomes that fill in all the gaps? Do you remember that great dinosaur movie from 1993 where they had dinosaur DNA, but it wasn't a complete DNA? And they filled in the gaps with frog DNA. Well, that's kind of what this second model does. It fills in the gaps with a probability distribution. Think of it as filling in the gaps. So what happens? We reach in and we pull out one of the players. We reach in and pull out the goalie. And we say, okay, now, what are all of the possible attempts? What are all the possible defenses by the goalie? Do you see how the second model is more complete? It has more possibilities. Well, these are really just the two. One's Monte Carlo, one is bootstrapping. I'll ask you the question, which one do you think is which? Let's read this Monte Carlo right here. Involves generating a large number of random variables from a given probability distribution. So Monte Carlo is the second example that I provided, which is much more complete. We can run this thing hundreds of thousands of times. Now, look at the second diamond point. Useful when the number of random variables is too high to use ordinary methods. Oh my gosh, now. In level 1 and 2 and 3, we're going to talk about ordinary least squares regression. There's a learning module in level 1 on just simple linear regression. But then when we get to level 2, we're going to do time series. We're going to do ARIMA models. We're going to use Garch models where we have lots and lots of random variables. But even with climate change, like I said in the beginning, or USA Super Bowl, like I said in the beginning, or this World Cup example, which I just went through here over the last few minutes. There are so many random variables that makes Garch models and multiple regression models just not capable of being able to come up with some kind of a reasonable conclusion. So what do? We use this Monte Carlo simulation. Look at some of the examples. Estimating risk and return, Financial modeling. Oh, this is what I was saying earlier, estimating risk and return. So we have a client provides us with, let's say, $1 million of his or her capital. And they say something like, you know what, when I die in 14 years, I'd like to have $4 million. So we use all this stuff that we've been talking about. And then of course, a lot more material in levels 2 and 3 to be able to predict and estimate that end of period wealth. So estimating risk and return, financial modeling. Just think of an Excel spreadsheet to putting together with all of these input variables. But then this is going to be super important when we hit level 2. Lots of people, lots of candidates say that level 2 exam is the hardest of the 3. I'm pretty certain that I would go ahead and make that conclusion as well. When I left level 1, I was thinking, you know what, I'm pretty sure I passed that one. When I left level 2, I said to myself, man, I don't really have any idea if I passed or not. That was really difficult. And I passed. Maybe I was just that last person who passed. But level 2 is way more technical and way more mathematical. We're going to talk about derivative securities. We're going to talk about mortgage-backed securities. We're going to talk about bonds that have embedded options. And we're going to use this Monte Carlo simulation to help us. Now, here's a picture of exactly what I was saying. There's the history, right? And then there's today. And then we're saying, okay, here are all of the possible shots that the 5 soccer players can hit and 5 possible defenses by the goalie, all those things. And then look, turn your head sideways. Don't do it too quickly. I don't want you to get vertigo. There's a normal distribution. Now, how do we do this? So let's suppose that we have a client and we want the split between stocks and bonds, 70-30 split over a 20-year period. All right, how are we going to do this? So step 1, specify the quantity of interest in terms of the underlying values. All right, so what are we wanting to do? We want that final portfolio value. How do we do this? Well, we continuously compound returns over that time period. Start with 100,000, so 70% in equities, 30% in bonds. Specify a time horizon. Now, what did we do back in my World Cup example? My time horizon, oh my gosh, it was, how long does it take you to do this? I mean, that's 20 minutes or so, right? But in finance, the application can extend to longer time periods. Now, here I was just referring to individual clients, but we'll talk at length about institutional clients. What if we're running a pension fund and we don't really want to maximize end of period wealth? What we want to do is minimize the probability that we're not going to have enough capital to meet all of our retirement obligations on a monthly basis over some long time period. And remember, if we're running a pension fund, we're running it for essentially an infinite time period, right? We have all these workers. Some of them are 60 years old, retiring soon. Some of them are 20 years old who may never get to retire, right? So we have to worry about a long time period. All right, so 20 years, we can divide the calendar into sub-periods, however many time periods we want. We could do this, we could do it quarterly, monthly, daily. We could do it continuously if we wanted to, but that's probably not too reasonable. All right, we need to make distributional assumptions. What does that mean? Hey, how about we pick a 7% average return for stocks, 3% average return for bonds, with 15% standard deviation and 5% standard deviation for stocks and bonds. All right, so here is an extra input that we have to come up with based on what? Based on, history, based on our understanding of the economy, based on all sorts of fun things. That's why when we're done this first topic, we're going to move into the topic of economics here in level 1, and we're going to talk about all sorts of macro and microeconomic variables that are going to lead us to be able to figure out where the economy is going so we can come up with a reasonable, well, in this case, it's 7% and 13%, right? All right, so look in the purple, there's our equation for the change in portfolio value. We did this in a different learning module. Z is the standard normal random variable. standard normal. Oh, wait a minute. We're assuming a log normal distribution, so the Z table is appropriate. So what we're going to do is we're going to use the program to draw 20 random values. So we'll just reach in, and just like we're pulling out a soccer player and saying, okay, this was his or her history, or this is his or her total distribution, we reach in and find out, okay, here's a stock, here's a bond, here's a stock, here's a bond. We do all that stuff. 20 random variables. All right, we convert that, 20 year, that makes sense. And from these observations, we create a sequence of 20 portfolio values, and then we take the average and we divide by 20. So that gives us our 20 out there at the end, right? 20 out there at the end. And then we're going to do this. Well, look at the bottom. That's one simulation. Then we're going to do this, well, however many times we want. How many times do you think the World Cup analysts could perform a simulation from the very end of the second overtime to when the announcers come back on over what is that? Let's say 120 seconds of commercial time. I don't know, a couple thousand probably. So then what do? We get the mean, the median, and the percentiles, and it provides us with all of these potential outcomes. Now, I'll say this regularly, the Institute loves to have as its last LOS in many of these learning modules, they say something like, all right, in these first 5 or 10 learning outcome statements, we did all this really, really great stuff. What are its problems? So lots of LOSs at the very end say something like, tell me the disadvantages of what we just did. What are the limitations of what we just did? What are the restrictions of what we just did? Well, look at the second teardrop point there. Fairly complex. I mean, think about it. It pulls out a probability distribution of a particular soccer player. Suppose this soccer player is left-footed, but during the course of that match, this particular soccer player got kicked in the ankle, the left ankle. Nowhere in that probability distribution is there a measure of how that is going to impact the current kick. All right, so fairly complex. So think about what this means for portfolio management. Suppose we were running a Monte Carlo simulation let me make sure I pick the month correctly, in June of 2019. And we do it over 20 years, just to be consistent with this particular example. We do it over 20 years. Well, who in their right mind would have had COVID in that model as a possibility? Well, pause. Comma, I'm going to say to you, hardly anybody had that back in their model in 2019, comma. However, lots of us, we're learning this in the CFA program, is that we need to understand these impacts of low probability, high consequence events. And so in 2019, somebody should have had that in there. But remember, if you don't put it in the model, it's not going to be in the model, right? So fairly complex, may cause errors, and they're really not exact figures because they are statistical estimates. Maybe the underlying assumption, the underlying distribution is not normal. Yeah. What are the strengths? Oh my gosh, the strengths are that this provides us with a wealth of extra information in executing the terms of the investment policy statement. So what does the Institute tell us in this reading? Estimating risk and return, and it helps us to determine the value of complex securities. Oh boy, we'll learn more and more about that, especially in level 2. All right, do I need to tell you about bootstrapping? Bootstrapping is the first example that I gave you. We're just going to pull out a player and repeat a penalty shot that he or she has kicked in one particular instance during their history, right? Repeatedly drawing samples from the originally observed data sample. It's a commonly used method. It's called resampling. Number of repeated samples determined by the researcher. This is exactly what we're saying. So the true population is going to be the same thing as the estimated population. And so just look at the bottom here. There's the true sampling distribution, and then there's the bootstrap sampling distribution. Boy, I tell you what, if you look at those two really quickly, you're going to say to yourself, you know what, those are really, really close to each other. And in fact, bootstrapping is a really good method. It's not the perfect method, but you know, it gets you close. It gets you pretty close. Yeah, the fundamental idea is to construct this sampling distribution based on whatever goes inside of the box. If we're doing, in our example, what was that, 70% and 30%, you know, we've got stock returns and we have bond returns. The more bond returns and the more stock returns that we have, then the better insight that we're probably going to have about computing that future value. Yeah, look at the bottom point there. Sampling treats the randomly obtained sample as a surrogate, as a proxy for the real population. Yeah, they both lean heavily on repetitive sampling. That makes sense. Considers the resampled data set as a proxy. We just said that in the previous one. Yeah, Monte Carlo generated random data, predetermined statistical distribution. That's what I was talking about in filling in the gaps. Now, of course, those of you who love those dinosaur movies, which I'm just a huge fan of all those dinosaur movies, is that using frog DNA, that caused some problems. Do you remember the problem that it caused? Oh, they all thought that all the dinosaurs were female, but it allowed them to reproduce because of frogs. I don't know anything about science, so. All right, it's the simulation process using bootstrapping is similar. So that's the key word, right? That's what we're doing. What's the difference? The difference is that we're just taking out actual historical returns for bonds or stocks or goalies or soccer players. So what are we doing? Same thing, step one, same thing, step two, same thing in step three, except we're using what the Institute calls the empirical, the actual historical distribution. We can do this 20 times, right? And we're going to do this over and over and over again. We're going to do it. And then we have those future values and we divide by 20 if we divide by 20, if we pick 20. And there's our one simulation trial. And then we do this many, many times. That takes us through here. So what are the key things about this learning module? Yes. Normal, log-normal distributions. We're up to date on that. Monte Carlo and bootstrapping. Just remember my World Cup example, and I think you'll be super fine. So, hey, thanks for watching. What I want you to do now is go to the end of this learning module, do the handful of questions there. Should be pretty straightforward. So, good luck studying. Thanks for watching.